Hello, okay, welcome to my third video, which will be covering photolithography. Okay, so first, I'll go through a non-technical summary, then I'll give a very brief overview of photolithography, followed by introduction to exposure sources or sources of light in photolithography. Then I'll cover the different types of photomask. Then I will cover resolution, depth of focus and contrast. Then after that, I will cover basically resolution enhancement methods. Then I will cover a photoresist chemistry, followed by photolithography process flow, and lastly, I will cover photolithography in action. So, okay, first for a non-technical summary. So, you know that computer chips, right, have very complex patterns in them, right? We covered that in the previous video. And to achieve this very complex pattern, we need a method of patterning, right? Patterning on the surface of the whatever material that we are constructing the chip from. And so the method that is used in semiconductor fabs to achieve this patterning is called photolithography. And so in photolithography, normally what we have is that we have a very complicated and advanced machines that conduct this process by companies such as ASML, which produce the most leading edge photolithography equipment. And so the reason why some countries have fought over this the export of this equipment is because this equipment and the quality and precision of this equipment is absolutely crucial to producing like computer chips of the highest quality and best performance. Okay. So that's enough of the non-technical summary. Let's go into an overview of photolithography. So as what I mentioned, photolithography is a way to achieve patterning in semiconductor device fabrication. So normally what is done is that some certain layers sometimes are added onto the surface of the wafer. Then after that, what we call a photoresist is actually deposited on the surface of the wafer, following which we basically expose the photoresist, and this is a step in which a pattern, right, is basically imprinted onto the photoresist via UV light, followed by a development of the photoresist as well as like solidifying the photoresist, and then with the pattern defined on the photoresist layer, we can do whatever processes subsequently to carve this pattern or basically imprint this pattern onto the wafer substrate itself. Okay, and so during this exposure process, what we have is that we basically shine a light through a mask. So this mask basically blocks out certain areas from preventing light to pass through certain areas, and this is able to imprint a pattern of light exposure, on the photoresist layer. Okay, so so now I'll introduce types of photoresist. So I think there was a typo earlier. I'm not talking about types of photomask, but types of photoresist. So there are two types of basically photoresist. Basically a positive resist and a negative resist. So the difference is like which area gets washed away after the pattern is imprinted by light. So light just imprints rather a certain pattern onto the photoresist, right? It doesn't remove any of the material. So after that, we need to use something called a developer solution to remove certain areas of the photoresist. And so in a positive photoresist is the areas of the resist that has been exposed to the light that gets washed away. So we call this a positive tone or positive photoresist. Whereas in the negative photoresist is the areas that is not exposed to light that gets washed away. So you can think of it as the areas exposed to light get solidified and fixed there. Whereas for the positive photoresist is the area that's exposed to light that gets weakened in a sense, right, and then washed away. So however, in industry, most commonly we see positive photoresist, right? Negative photoresist are slightly less common. So in today's video, I'll mainly be covering all the examples. Will be covering positive photoresist. So for a photolithography machine, right, we do need a light source. We need a source of the UV light. So what has been the trend over the years is to get light sources of smaller and smaller wavelength of the UV radiation. Why is that? So you'll see later, but basically a smaller and smaller wavelength is able to result in a better and better resolution. So resolution is like your photo resolution. It's how small your features can get without being too blurry, right? So of course, if you can get better resolution, right, you can get more sharper features, and sharper features means you can get smaller, right, features that you can define on your wafer, and that normally can result in the formation of more advanced devices that have better performance. So initially, in the very early years, right, they use basically the mercury arc lamps, to produce the UV radiation. However, the wavelength of the UV light produced is pretty large. It's like 400, 300 plus nanometers. So the next step in the development was this excimer lasers. So excimer lasers, there are two types that results in two different kinds of wavelength. Right, one of them 248 nanometers. The other one is 193 nanometers. And beyond that, excimer lasers, right? Excimer lasers are sometimes what we call DUV, right? Deep ultraviolet wavelengths of light source. However, after that, right, they developed, or rather ASML, the company developed what is known as EUV, right? Extreme ultraviolet. Why extreme? Because it's extremely small wavelength of only 13.5 nanometers. And there's a very special and difficult to master light source that is driving these EUV light sources. Okay, so let's go to the most original, right, the oldest source of UV light for lithography, and that is a mercury arc lamp. So what happens is that basically mercury is excited by the application of a certain electric field, and when it's excited, it's able to produce, right, to emit light of certain wavelengths. So note that these wavelengths of light are sort of quantized, right, because they correspond to an electronic transition in the mercury atom. So we do not use all of the wavelengths, right? We selectively use the I line and the G line for photolithography processes. So we just use a filter that's able to selectively filter out these wavelengths of light, and we use these wavelengths for basically your photolithography process. So it's very important that the light source is essentially a monochromic light source. So a light source that only contains one wavelength, because different wavelengths of light will have different behavior, right? And we do not want like basically like having like multiple images on your photoresist, right, that comes from different wavelengths of the light source. So we just want to have one wavelength of light, and so we either choose the I line or the G line by use of a filter. And the next technology is the excimer laser. So excimer, you can think of it as an excited dimer. So basically what happens is that we have a combination of two kinds of gas, normally a noble gas and a halogen. So a noble gas and a halogen is combined. However, normally, right, the noble gas and the halogen do not combine without any external stimulus, any external input of energy, because that combination is not a chemically spontaneous reaction, right? It's basically it's a reaction that absorbs energy. So, however, when we basically have a source of excitement, right, we can form this excited dimer, this excimer, and when this excimer decays, right, because it's an unstable state, right, when this unstable excimer decays back to ground state, which is back to the individual atoms, it releases a photon of a fixed wavelength, in the UV range. So for basically this one KRF, it emits at 248 nanometers. But if you use ARF, so you change your noble gas, right, into argon, you can get a smaller wavelength of 193 nanometers. So this is the principle of excimer laser light source. And for EUV light source, it's like the most advanced of them all. So basically what happens is that there's a stream of thin droplets, and a pulse laser is used to excite these thin droplets. And when the pulse laser hits upon the thin droplets, it basically excites the thin droplets into higher electronic states, and the decay down from the higher electronic states to the lower electronic states releases of course a photon of light of a defined quantized wavelength. And so the reason for having a pulse laser is because we want to excite, then give it time for it to de-excite, right, before exciting it again. So the pulse, right, allows for this periodic excitation, de-excitation, and so on and so forth. And it is in the de-excitation and the relaxation phase where it emits the photon of light. So yeah, this is an extremely difficult to master technique, because we need extremely advanced optical equipment to get this pulse laser to excite the thin droplets very precisely. So recently there have been certain developments reported in the news by basically a Chinese company or university linked company. If I'm not wrong, it's Harbin University. I may be wrong, but it's developing alternative EUV light source, where instead of using a pulse laser to excite the thin droplets, if I'm not wrong, they are using an electric field. So the benefit of this is that um, you don't need the kind of advanced optical instruments to get the pulse laser. And I think the efficiency, the energy efficiency is higher, because when you have a laser impinging, basically hitting your thin droplets, right, light is not always absorbed, right, it can be reflected. And when the some of the laser light is reflected, it represents a loss, right, inefficiency, because not all of the energy input is used to excite the thin droplets. So theoretically, if you use the electric field, right, you can more efficiently excite the thin droplets, thus resulting in a more efficient UV light source. However, there are also basically implementation issues when we use electric field to excite the thin droplet. It's more difficult to control in many ways. So from what I know, basically this is still in the product development stage. It's still quite a far distance away from commercialization. And so now I will share a bit on the photo mask for UV and DUV lithography. Oh yeah, so in this case I also share like different types of photo masks as well. So I don't think so it's not really a typo. I'll cover both different types of photo resist, which I covered, and also now I'm covering different types of photo masks. So for UV and DUV lithography, right, we can basically use a photo mask that is transparent to the UV light that is passing through it. So it's often like let's say a certain metal, maybe a certain metal like chromium or something, deposited on, let's say, a silica substrate, so that is transparent to the wavelengths of the UV light that is being used in this case. And yeah, so the pattern is carved on that mask, right, on, let's say, the metal layer, like your chromium layer, or your, let's say, what, tungsten layer or something like that, is carved using an electron beam. Is using an electron beam, because electron beam is able to basically carve out small enough patterns for your photo mask. So there are certain companies that are like specialized just making photo masks for eventual use in like fabs such as like TSMC, Global Foundries, Micron, so on and so forth. And yeah, so in this case, sometimes we will see a pellicle on top of the mask, and the pellicle basically protects the mask from any debris. Because if there's any debris, any particles that drop on the mask, right, it will basically affect the pattern, right? Because it will make the mask like it will basically have extra like areas on the mask that's blocking out light that's not supposed to. However, when this, you may ask, right, when these particles drop on the pellicle, right, isn't it like also as bad, right? But the good thing is that the pellicle is not at the focal distance. It's not at the focal distance. So even when a particle drops on the pellicle, the kind of impact it has on the eventual image is less. For example, right, if you have like a few particles of dirt on your spectacles, for those who wear glasses, right, you do affect your image that you see a bit, right, but it's not like very clear, right, there's a particle there, maybe a certain spot is slightly blurry, right. Same thing. So if the particle it drops on the pellicle, right, it wouldn't degrade the image so much compared to if it drops directly on the mask. So however, for EUV lithography, the kind of photo mask that we're using is different already, because for EUV wavelength, there are no or very few materials that are transparent to the EUV wavelength of light. So we cannot pass EUV light through something, right? In this case, through photo mask, we can't do that, because any material they make of the photo mask will absorb EUV light, because it's of such a small wavelength that very few materials are transparent to it. So basically, the optics that is used in the EUV exposure machine is reflection based optics. So the lenses are all like mirrors that have maybe a certain curvature to achieve the focusing of the light that gets reflected off it. So as a result, the mask must also be placed on such a mirror, right? The mask must be placed on such a mirror. So we see that the mask, like, often is chromium, is deposited on a mirror, and this mirror is quite interesting also. This mirror is basically is a very precise stack, atomic stack of alternating molybdenum and silicon atomic layers. So why do we use this? Because it's very interesting, because the distance, interplanar distance between your molybdenum and silicon layers is just nice half the wavelength of the EUV light, half the wavelength of the EUV light. So half of 13.5 nanometers. And so by Bragg's diffraction equation, you'll see that this exactly results in constructive interference, resulting in very high efficiency of the reflection of EUV light off the surface. So sometimes we call this a Bragg's reflector, because it reflects very well by the principle of this kind of Bragg's diffraction constructive interference. Yeah, so it's very interesting why we use this particular material of this particular structure for our mirrors in the EUV machine. And so now I will share a bit about diffraction effects in photolithography. Because like, you may think, right, that let's say if we use a photolithography machine, the mask, if you define it perfectly, right, can we get the perfect image on the photoresist, right? You may think, if the mask is made well enough, oh, the image should be perfect. However, unfortunately, that's not the case. So I'll share a few types of photolithography. So we can potentially make the mask very close to the wafer. Alright, very close to the wafer, in contact or very close to the wafer, and so the image on the mask kind of gets directly transferred onto the wafer by the UV light passing through it, right? However, that is not what is done in industry. Why? Because the mask is not the smallest size we want to define. The mask is often bigger. The size of the features on the mask is often bigger than the size of the features on the wafer that we want to define. So we often, right, basically have a certain distance between the mask and the wafer, and between them we have many different lenses that focuses the light, the image, right, into smaller and smaller and smaller dimensions until eventually it goes onto the wafer. So for example, here in the EUV machine, all these mirrors are lenses, so they are focusing the light smaller and smaller and smaller, or rather this way, smaller and smaller and smaller before onto the wafer over here. So however, the problem is that when like light passes through an aperture, because the mask is full of like holes, right, where you want the pattern is full of like the holes, right, the holes that you pattern out. And so when light passes through these apertures, right, diffraction occurs. You may have learned in secondary school this idea of diffraction through a single slit. So effectively, that's what happens. So when diffraction occurs, right, what happens when the light passes through the aperture? It spreads out, right? You should know that diffraction causes a spreading out of the light when passing through the aperture. And so if you have a lens of like a finite dimension, right, it's inevitable that you will not be able to capture some of the light that has been diffracted to higher orders, right, that has been spreaded out further away, right, further away at a higher angle of diffraction. So unfortunately, that means that you're losing some information from the light. You're losing some information. So when you eventually focus down into the image to be imprinted onto the wafer, you will see that basically the features are not as perfect as what you want, as what you would expect from the mask. So yeah, so this is the idea of resolution of photolithography. So as you can see, when the light passes through an aperture, it undergoes single slit diffraction, right? And so there's a spreading out of the waves and the formation of these higher order fringes. And when your lens of a finite size, right, is unable to capture all of these higher order fringes, we encounter basically a loss of information. And so we can actually use a Rayleigh's criteria, which you may have learned in basically in pre-university, to actually find out what is the factors that affect the resolution of photolithography. So I will not go into the derivation of this, but it's not that difficult. But basically, you can derive like a relationship between resolution, right, R, and lambda, and the size of your aperture. In this case, like it can be like considered the size of this objective lens over here. The size of this objective lens is what I call the numerical aperture NA. And so we want a small value of R. Because small value means you can define smaller features. We can resolve smaller features. So when we want a smaller value of R, what do? We can either decrease the wavelength or increase the aperture size. So that is why, right, over the years, photolithography has evolved to use smaller and smaller wavelengths of UV light. Right, smaller and smaller wavelengths of UV light, because we want to get smaller and smaller features that we can resolve. And so in this case, theoretically, right, for let's say a point source and an aperture of a very perfect geometry, the value here of this, let's say, constant is 0.61. However, of course, in the real setting, right, our apertures are not like perfect rectangles or perfect circles, right? They are like of different patterns, and the source is also non-perfect. So we basically generalize the constant to be something called K1, which is something that depends on like the features of the mask and also the properties of the photolithography machine. So it's something that can only be obtained experimentally, and it's very difficult to calculate. So the effect of numerical aperture, of course, is that the larger the aperture, the better resolved your features can be. And this makes intuitive sense, because the larger your aperture, the more of these higher order fringes you can collect, right, and you can focus into your image. And so therefore, the better defined your features will eventually be in your image. So another very important parameter, optical parameter for photolithography, is this idea of depth of focus. So depth of focus is basically what is the kind of distance you can deviate away from the focal point and your image is still relatively in focus. Because for example, if you like go all the way here, your image is very not in focus because your beam has spread out already, has spreaded out already. And if you go very far on top, the beam hasn't converged yet, so your image is also very not in focus. So in a certain region over here, right, we can define, let's say, a acceptable amount of focus, and the depth at which, right, the image is still fits our requirement of being so-called in focus is called the depth of focus. And so it's a plus minus, because plus minus above and below the focal point. And so I wouldn't cover the derivation, but basically it's given by this expression, which is very similar to your expression for resolution, just that it is dependent on the square of the numerical aperture. So if you have a very large lens, right, I have to emphasize here that while resolution we want as small a r as possible, for depth of field we want as large a depth of field as possible. We want as large a depth of field as possible because we want the image to remain in focus for a thicker layer. So when we have a large lens, right, we can see that the beam diverges, right, very quickly. So your depth of focus is very small. However, when you have a small lens, a small NA, right, the beam diverges after the focal point less quickly. So we have a larger distance at which the image is still somewhat in focus. So why do we want a large depth of focus? Right, we want the large depth of focus because we do not want our photoresist to be too thin. We want to have a relatively thick enough photoresist, and yet throughout the photoresist, the image is still in focus. Because remember, we are imprinting the image on the photoresist, and we want the image to be imprinted through the entire thickness of the photoresist, so that when we develop the photoresist, right, the patterns gets dissolved away throughout the entire thickness of the photoresist. So, and we cannot have too thin photoresist, because remember, photoresist is used as a mask for later processes. It's used to define certain features for later processes. If your photoresist is too thin, your subsequent processes can erode away the photoresist, and erode away the patterns of the photoresist, resulting in a degradation of the kind of precision of your subsequent process steps. So yeah, we do want a very good depth of focus, and we do see, right, that there's a conflict between resolution and depth of focus, because they both have very similar forms of the equation. They are both dependent on lambda and inversely dependent on a numerical aperture. So often case when we try to strive to get better resolution by like shifting the wavelength smaller and smaller, and increasing the numerical aperture, we end up degrading the depth of focus, which is a big problem as well in the practical applications of lithography. And another kind of optical parameter that we need to bear in mind is the idea of contrast, also, which is defined in terms of this kind of MTF, the modulation transfer function. So basically, the MTF is defined as such, and so the ideal case is that your Imax, your maximum intensity of your image, right, actually should be this one because on the wafer, right, your maximum intensity of the image in the wafer is ideal case is 1 when it's supposed to be unmasked, and when it's supposed to be masked, right, by the photo mask, it's supposed to be 0. So the ideal case is Imax is 1, Imin is 0, and so MTF, right, is large. So we want MTF to be as large as possible. However, when the feature size gets smaller and smaller by the principles of optics, right, the MTF that you can get, alright, it gets smaller and smaller, and that means our contrast gets worse and worse and worse, and that's not desirable, because that means that certain areas that later you want to develop and dissolve away may not get fully dissolved, and certain areas where we want to not to get dissolved away, right, starts to get dissolved away a bit. So the gradient, or basically the profile between where we want to keep the photoresist and where we want to dissolve the photoresist becomes less steep, more gentle, and that results in, let's say, a distortion of the feature dimensions that we want to pattern on the wafer. And so now I'll cover a few optical techniques to achieve a resolution enhancement, because remember I mentioned that resolution and depth of focus is a conflicting requirement. However, there are methods at which you can balance out this conflicting requirement and achieve some form of a better performance that doesn't sacrifice too much of one of them. And one of the method is basically immersion photolithography. Immersion. So what happens is that there's a layer of fluid, right, that's why it's immersion, right, between the lens and the photoresist. So I'd like to show you basically the red line over here. The red line is over here, where between the lens and basically the wafer, there is basically air. So air has a basically lower refractive index, right? So when the light goes into the air, right, it undergoes, right, refraction, and so the angle becomes larger. And what happens when the angle is large, right? The depth of focus degrades because the beam then diverges very fast when we move out of the focal point, and so that represents a degradation of the depth of focus. However, when you have water in between, water has a very good similarity with the refractive index of, let's say, your photoresist and then your silicon. And so when you have the water layer in between, right, the ray of UV light, right, doesn't get refracted as much, right, and so we see a smaller angle of refraction and therefore a better depth of focus. So we improve the depth of focus, right, even while maintaining the same resolution. And in fact, we can actually also like use this to increase our numerical aperture of the lens, because one main problem with increasing the numerical aperture to be too large is this idea of total internal reflection. Because if your angle of your angle of your numerical aperture, right, the angle of the size of the angle is too large, right, what happens is that there tends to be total internal reflection at the interface between the lens and the air gap. And so that's not good, because we want the light to pass through our lens, right, not get reflected at the lens boundary. And this is basically remediated when we have the water layer, because the water has a much closer refractive index to the lens. So you have this N2 over N1 ratio approaches that of 1, and therefore your critical angle approaches that of 90 degrees. So we can have very close to 90-degree kind of angle of incidence without undergoing total internal reflection. So we can basically expand the numerical aperture of the lens to be much bigger than the ones that we than what we could achieve without this immersion technique. And another area that we use to improve, let's say, the profiles, right, and the definition of features in photolithography is this idea of anti-reflection coating. Because when light passes through the photoresist, not all will be absorbed by the photoresist, right? Some will reflect off the silicon surface. And so when we have an incoming light and a reflected light, right, incoming wave and reflected wave, right, this is very similar to what we learned in secondary school, right, of like let's say a sound wave in one in a pipe that's open on one end, right? So what happens is a standing wave is formed. Standing wave is formed within the photoresist, and so that's not good. Why? Because it result in, right, your node and anti-node forming this kind of wavy pattern on the walls of your photoresist after you develop. And so we want to avoid that. And one way to avoid that is to have a back anti-reflection coating, also known as BARC, at the back layer. And so that reduces reflection by introducing destructive interference of reflected wave. So if, right, with a certain refractive index of the back, we choose an appropriate thickness of the back layer, right, the reflected light, right, is able to undergo destructive interference with the light reflected over here. So the light reflected at the interface here versus the light reflected at the interface here, right? These two basically these two rays of light have a phase shift that will result in destructive interference between them, and so that reduces the intensity of light reflected off the interface. And so you can see that as we increase the thickness of the layer, right, there's an optimal thickness where basically the destructive interference is most happens most exactly, and that is the thickness at which we would want to deposit our anti-reflection coating layer. And so another technique to improve, let's say, the defining of the patterns in photolithography is this idea of OPC, or optical proximity correction. So if we were to just pattern the pattern they want to pattern on the wafer using a mask that follows exactly the design rule. So we call this the design rule. We want this pattern in our eventual wafer, right? And if we use a mask that's exactly the same shape as the pattern, the design rule, right, we tend to get poor imaging. So for example, over here, we tend to get, like, let's say a curved edges here, right? So this area lacks your irradiation of light, and this area, the red areas, have too much irradiation of light. So what we can do is that we can break free of this idea that the mask must follow the design rule. We can make the mask, right, open a hole in the mask, for example here, to allow this part, right, more light to enter, because we know that over here, right, in the previous case, right, this area is not irradiated with enough light, right, there's a curved edge, so we open a hole here so that more light goes through here to cancel the effect out, and we then fill up a notch here to block some of the light from reaching this area, because we know that in the previous case too much light has entered into this curved area over here. So basically, by applying OPC rules on the mask, right, we can actually achieve eventual patterning that's closer to the design rule. So even though the mask deviates from the design rule, the eventual pattern we get is closer to the design rule because of this optical correction that's been involved. So this is a very smart way of achieving a better patterning of features, and this is very important for small features where your basically your photolithography becomes more and more difficult to be able to pattern these features precisely. So now I will cover the chemistry of positive photoresist. So the chemistry of positive photoresist. So for positive photoresist, what happens is that the areas that are illuminated by the light, right, eventually gets dissolved away. And so how come only the areas illuminated by light gets dissolved away, whereas the areas blocked, alright, the areas that does not receive any light is not dissolved away? And that's because a chemical reaction, right, basically a photoactivated, right, chemical reaction has to have happened in the areas that's been illuminated by the UV light. And so we shall look into what is this photochemistry in detail. So for G-line and I-line resist, right, the photoresist is primarily made out of this polymer over here called Novolac. Novolac is a certain kind of polymer, and this Novolac resin basically has a certain dissolution rate. However, we need to add something into the resin that is photoactive, that like basically interacts with light and changes with light exposure. And so that is what we call the DNQ. Right, is basically a chemical term. DNQ, photosensitive molecule, is added in. And so basically what happens is that it's irradiated. When it is irradiated with light, right, it can undergo a rearrangement reaction to form a carboxylic acid. So from something that is insoluble in anything, right, because in any in not in anything, insoluble in, let's say, in an alkaline solvent, for example, right, this is insoluble in an alkaline solvent, right, because it is not in an aqueous alkaline solvent, because it's a organic molecule that is very nonpolar, right, so it will not dissolve in an aqueous alkaline solution. It's a nonpolar molecule, right. What happens? It becomes a carboxylic acid molecule. A carboxylic acid molecule readily dissolves in the alkaline solution, right, because we can undergo an acid-base neutralization reaction. So effectively what we see here is that when we add the sensitizer to the Novolac resin, right, the dissolution rate drops, right. However, those areas that are illuminated with light, right, the dissolution rate is very high. So effectively we can selectively dissolve the areas that has been illuminated with light, because the DNQ molecule has undergone basically a photochemical reaction to become something that is able to accelerate the dissolution of the photoresist in the developer solution. However, for DUV and EUV resist, the chemistry is a bit different. So we have basically what we have is still a polymer to act as a photoresist backbones and certain groups bonded to it. And when there is a light that is shined onto the photoresist, what we call PAG, right, a photoactive group, right, becomes, right, a certain acid molecule. So you can see over here that this is the PAG, and it undergoes a photochemical reaction to become a strong acid. And that's it for the exposure, right? That's it for the exposure. So that's why after the exposure, you have to heat up the wafer to trigger a catalytic reaction. And in this catalytic reaction, the acid, right, the protons, the acid that was generated in the previous step, would then undergo chemical reactions with the groups that are attached to the polymer chains. And when the groups that are attached to the polymer chains get modified by this acid reaction, right, it makes the polymer chain easily dissolve in the developer solution. And so this is a catalytic reaction. The H plus is consumed and regenerated, and then when it reacts with the next group, consumed and regenerated, consumed and regenerated. So there's a very high photo efficiency of this reaction. So as a result, this resist is more sensitive. You only need less like UV radiation, and it can trigger a very efficient chemical reaction to occur. So for your information, this is the catalytic reaction chemistry. So with the addition of the H plus that was already generated in the exposure step, basically you can modify, you can react these functional groups that are bonded to the polymer, right, and basically make the polymer more easily to dissolve in the developer solution. So let me talk about resist contrast. So we just now talk about optical contrast in the optical image, but there's this idea of resist contrast also, because uh, for the dose that you're exposing the resist to, right, where at what dose does the resist, let's say, dissolve completely? Is it a steep drop, right? Like under a certain dose of light exposure, the resist completely doesn't dissolve, and then there's a critical dose at which all of them dissolve, right? Is it like that? Of course, that's the dream, that's the ideal. However, in many cases, that's not the case, right? There's a certain gradient to the graph, right? There are certain doses of exposure where you get some resist dissolve or some resist remain, and so that's not ideal. So the ideal case is when the d naught, which is when your is the exposure level at which dissolution starts to occur, right, is equal to df, which is the exposure dosage at which dissolution is complete, right? We want the ideal case is we want the d naught to be equal to df, and so in this case gamma, which is like the contrast parameter, is basically goes to infinity. We want that ideal situation, right? Df equals d naught log 1 0, 1 over 0 is infinity. So of course infinity is impossible. We just want gamma to be as large as possible. And similarly to the MTF function that we saw earlier, we can basically define a CMTF, critical MTF. In this case, it's like a chemical MTF that is for the resist contrast, right? And if we define it in this way, we want the CMTF to be equals to 0, because we want, once again, dF to be equal to d naught. So there's two sources of contrast now, one from the optical image or optical contrast, and one from the resist behavior. And so these two contrasts interact with each other. If you have very good optical contrast, the MTF is very good. Then your resist contrast, there's more tolerance. We can accept it to be worse, right? And conversely, if let's say your optical your resist contrast, rather your CMTF is very good, then there can be more leniency in your optical contrast, right? So you can see this over here, right? The red color is your dose, so the red color represents the 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 contrast in your optical image, right? So very sharp means that your optical image is very good. This area is completely not exposed to dose, this area is completely exposed to dose, and the gradient is very steep. So you can see that as your red curve degrades, right, that means as your optical contrast, your MTF degrades, right, your resist kind of pattern, right, eventually the quality of the pattern degrades, because we want very steep, we want ideal 90-degree sidewall, right? We want very nice patterns. However, as your basically your MTF, your optical contrast degrades, right, the profile becomes more and more inclined, which is not what we want. However, now we can also take a look at the case of how we can resolve this by using a photoresist with a better contrast, right? So df and d naught, right, once again is basically the same definition as over here. So when your df and d naught is very far apart, right, it represents a poor CMTF, right, a poor resist contrast. So in this case, right, which is the gray color area, we get, right, very gentle slopes, which is not what we want. However, if you manage to shrink df and d naught together, we manage to shrink it together, so it represents better CMTF, better resist contrast, right? Only at this spot, right, at this spot, let's say the resist fully dissolves, and at this spot the resist starts to dissolve. So we see that the incline of the side wall of the resist, it becomes much steeper, right? Take a moment to look at this graph more closely, right? Originally, right, this is where your resist completely dissolves, and this is where your resist starts to dissolve, and so your gradient is very gentle. But if we shrink the space between a df and d naught, if we make the resist contrast better, right, this is the area where the resist fully dissolves, this is the area where the resist starts to dissolve, the gradient becomes much steeper. And so even with the same pretty lousy basically optical contrast, we can still achieve a better resultant profile in our photoresist by having a better photoresist contrast. So Aside from contrast, there are other resist properties to consider, like the resolution of the resist, which is different from optical resolution. Right? Resolution of the resist is like how thin a line the resist can reproduce from an area image, which of course depends a lot on like, the development process of the resist, right? And which also depends a lot on the resist chemistry. And the next one is sensitivity. So it's basically the energy or like the dose of incident light needed to expose the resist, so that the subsequent development will like dissolve where it's supposed to dissolve and not dissolve where it's not supposed to dissolve. And so this is related to the efficiency of the photochemical reactions that happen during exposure. Right? The more efficient the photochemical reactions, the less dose of light we need to illuminate the resist to achieve the good development outcome. And lastly is the resistance of the resist to subsequent steps that is supposed to mask. For example, if you have a very energetic etch process after that, we want the resist to be able to resist, right, these etch processes, right? This so that the areas that's masked by the resist will not be etched away, and only the areas exposed by the photoresist will be etched away. So now I will cover, right, this process flow of the photolithography. So there are many steps, and so normally there's multiple machines that's used, right? Machines used for coating the photoresist and developing the photoresist. A machine known as a scanner to expose, right, the photoresist to the UV light. And of course, eventually when you want to clean away your resist, right, after it's done with what it's supposed to do, there's also resist stripping machines. So let's look at the first step, okay, which is surface cleaning and preparation. Actually, it's these first two steps, okay. So firstly, we want to clean the surface. So we want any contaminants and particles from the previous steps to be removed from the wafer surface, right? So this is a cleaning step. We'll cover more on cleaning, how cleaning is done in a future video. And the next is dehydration. Of course, it's basically removing the water from the surface of the wafer, right? And this is very important, right? We want the wafer to be dry. And then after we add the primer of HMDS, which is hexamethyl disilazine, and this is basically used to modify the wafer surface to make it more hydrophobic. Because normally for a silicon wafer, right, that is not like modified, at the surface there will be tend to be SiOH bonds, right? These bonds tend to be dangling at the surface, and these bonds, right, are polar bonds, so they are hydrophilic bonds. And what happens is that our photoresist is it's a non-polar, right? It's a non-polar organic molecule. It is a hydrophobic kind of species, so it will not be able to adhere well with a hydrophilic species. So we want to use this primer to modify the wafer surface to create this CH3, these methyl groups on the surface of the wafer. Methyl groups are non-polar organic groups that are result in the surface of the wafer becoming more hydrophobic. So this will help to enhance adhesion with the photoresist when it is applied. And so indeed the next step is the application of the photoresist by this process of spin coating. So what we do is that we drop a pool of photoresist fluid, right? So it's photoresist dispersed in the solvent, and then we spin the wafer to spread out the photoresist evenly across the wafer. And so basically depending on the viscosity of the photoresist solution, the spin rate will be different. So for example, for a highly viscous photoresist solution, so there's a high percent of the solid and low percent of the solvent, we want a high RPM, right, revolutions per minute spin, to be able to spread it out evenly. However, if the resist solution is very not viscous, right, it's not viscous, right, that means a lot of solvent, we cannot spin too fast. If not, all the resist will be spun out and none will remain on the wafer. So we have to tune the rate at which the wafer is spun to be a lower rate. So these are factors to consider. Yeah. Then after that is a pre-bake. So this pre-bake is used to evaporate any remaining solvent and to slightly densify the photoresist, and also improving adhesion of the photoresist to the wafer surface. So we see that we have to basically grasp a very good pre-bake temperature. We do not want the pre-bake temperature to be too low, where dissolution rate of the photoresist in later development will be too fast, right? That will make development hard to control. But we also don't want to bake too long, which causes dissolution rate to be so slow that dissolution in the developing stage will take too long. That is not ideal. We do not want to wait too long. So we need to get a good baking temperature that just nice, balances things. Then after that, it's time for alignment and exposure. So basically, alignment in this exposure step is extremely important, because the kind of features that are defining is like 10 nanometers, like maybe even 7 nanometers, very very small like dimensions of the features that you are defining. And so as a result, you need a extremely precise alignment. So what happens is that normally alignment mark is patterned on the wafer, and on the mask there's also likewise another alignment mark, and it is the alignment of both of these marks together that basically tells the machine that the wafer is correctly aligned and the exposure can happen. And that is basically how they align the wafer to ensure exposure is done correctly. Then after exposure, this is the step at which the UV light is shined on the wafer. After the UV light is shined on the wafer, um, it's time for the post-exposure bake. So it's not time for development yet, it's time for the post-exposure bake first. So what is the purpose of post-exposure bake? So for G-line and I-line resist, the main purpose is to smooth out the side wall of the resist to relieve standing wave effect. Essentially, we want to avoid this. And so by baking the photoresist above the glass transition temperature of the polymer, because it's a polymer, so it has a glass transition temperature, right? It allows the polymer to flow a bit slightly, because remember, polymer chains above the glass transition temperature is able to undergo a bit of flowing, a bit more free motion, so to round off the side walls to prevent this wavy standing wave effect from persisting. Right, so that's the main purpose for G-line and I-line resist. However, for chemically amplified resist, which is DUV and EUV resist, where we have this catalytic photoacid reaction, right, the post-exposure bake is absolutely necessary for the chemical reaction to happen, right? Because the exposure step only generates the acid, right? The acid still hasn't reacted with the polymer to make it easy to dissolve, right? The acid still hasn't reacted with the photoresist. This reaction needs to happen before before development can occur, right? We want the catalytic reaction to occur, and this needs to happen under a heating. So this post-exposure bake provides the heat required to drive this chemical amplification step. And so finally, after post-exposure bake, we can undergo our development. So wafer is developed oftentimes in an alkaline solution, but this also depends on the chemistry of the photoresist. And so it dissolves for positive photoresist. It dissolves the part of the photoresist that's been exposed to the UV light. And basically, the exposure dose that occurred during exposure step is closely linked to the development time required. So we want to have sufficient exposure such that the development time is not too long, because if the development time is too long, we can encounter things like overdevelopment, right? That is not ideal, because we basically have a non-ideal geometry profile, right, of the edge of the photoresist. And so finally, after developing your resist, is we post bake, so we bake it one more time. And so the purpose of the post bake is to densify and harden the resist, and also it improves the adhesion to the wafer. However, you have to take note, you have to be careful, because the higher the temperature of the post bake, right, the profile of the resist changes, right? Because these are above the glass transition temperature of the photoresist already. So the polymer chains can move, and when they move, they basically alter the geometry, right, the profile of the photoresist, and that may not be good, right, because it may distort the patterns that you want to imprint. However, post bake is still necessary to increase the densification, right, to densify the resist, to increase its resistance to subsequent energetic processes that it needs to mask. For example, ion implantation, plasma etch, these are highly energetic and damaging processes. So if your photoresist is not strong enough, right, it could affect subsequent processes. So how do we use the resist to pattern? I briefly covered this in the previous video already, when I covered like how resist is used to mask certain processes. So for example, let's say we want to deposit a certain pattern of material on the photoresist. So when it comes to like deposition, right, there are two ways we can use the resist to pattern our deposition. The first way is direct etch. So we first deposit the material that we have, a layer everywhere. Then we pattern the photoresist on top of it. Then we use the gaps that's patterned on the photoresist, right, to etch the layer below to form the pattern that we want. So that's one way. The second way is lift off, which is that the photoresist is first patterned on the wafer surface. Then only after the photoresist is on the wafer surface is the desired material deposited on it. And then after that, the photoresist is removed, and the material above the photoresist is also removed, is lifted off. So we call it a lift off method, lifted off. And then the desired pattern is left behind. So both methods are possible to be used. Yeah. but lift off generally tends to cause more contamination, because when we lift off the the film that's deposited on the photoresist, right, it could drop back on the wafer and things like that. It could cause particulate contamination, right? So we just need to take note of that. And so the photoresist itself, right, is removed by either by solvent dissolution, right, because it is after all an organic material, so it can be dissolved in certain organic solvents. Either that, or you can also use plasma etching in oxygen plasma to that is normally more for the cleaning, right? After you remove most of the photoresist by solvent, right, if any residue is remaining, we can use oxygen plasma to remove it. Why? Because photoresist is an organic substance. It can combust in oxygen. It reacts in oxygen to form CO2 and H2O, so an oxidation reaction, so that effectively removes any residual photoresist debris. Yeah. So now I'll cover ways to achieve, right, patterning of, like, let's say, sublithographic dimensions, dimensions that are even smaller than your resolution limit of the photolithography machine that you're using. One very simple method is multi-patterning. So we just pattern one pattern first, then pattern the other pattern, and because these patterns are close together, so effectively we get like double the density of patterns, right? Double the density, half the dimension, right? So this is actually, if I'm not wrong, based on what is being reported, is being used by certain companies in China, because they have been restricted from using certain lithography machines that has the best resolution. So in order to achieve such a resolution with worser machines, right, older technology that has poorer lithography resolution, they use multiple patterning to achieve these sublithographic dimensions. However, there's a problem with this, because you have to do the lithography step twice, which firstly increases the time taken, because lithography is a very slow process actually. Yeah. And secondly, it also increases the cost, because you need double the lithography dose, double the photoresist coating, and all that kind of things. So it increases the cost, reduces the increases the time taken, and also reduces the yield, because with more lithography steps, there are more areas that mistakes can occur, which will lower the yield of the manufacturing process. Another way to achieve sublithographic definitions is through the sidewall spacer method. So what we'll do is that we will use the lithography to, let's say, etch a certain pattern on, let's say, a sacrificial layer of polysilicon. So we call this a mandrel, so it's a sacrificial layer. Then we deposit a conformal layer of silicon nitride. The nitride layer is deposited conformally, so it basically follows the curvature of the polysilicon. That means on the side walls of the polysilicon, it is there. That's very important. Then we use an anisotropic etch to only etch in the vertical direction. So we don't etch in the side wall direction. So it leaves the side walls. The nitride still remains on the side walls. Then we selectively remove the polysilicon by etch. And what is left? What is left was the side walls. And these side walls are much thinner than the polysilicon mandrels that we defined earlier. So if, let's say, the polysilicon mandrels were defined at the limit of the lithography technique, we effectively define a dimension even smaller than that limit through the sidewall spacers. Yeah, so that is one very useful method that is used to define very small features, especially in more and more advanced technologies. So okay, this marks the end of the video on photolithography. So it's a pretty long video. I hope that it was insightful, and that it was a good learning experience. So in the next video, I'll cover on thermal oxidation. Yeah, thank you.